So in the last classes we discussed about AlexNet, then we talked about VGG and especially VGG 16 and 19 because these are the most used VGGs. Okay, so all these were good, they were good for their time, but what was the main problem that we were having? Well, as we increased the number of layers, we still had the problem of more parameters. So that means we had a chance of overfitting. We did not want that. We wanted something, a model that could go deep but would not cause us overfitting. And even though with VGG 16 and 19 they had 1 cross 1 convolution, but even that could not help that much. We still needed something more. So we came up with the next model, InceptionNet. So over the years, InceptionNet has even grown more and more, and we have InceptionNet V2, V3, and different version of InceptionNet. But for now, we will be studying V1, and then later on, we'll be going back and learning about V2 and V3. But for now, let us talk about InceptionNet V1. Okay, so first problem we knew about VGG 16 was even after batch normalization and ReLU and everything, we still had the problem of overfitting. But we know if we have to get more deeper models, more accuracy, we need more layers, and hence our parameters are going to increase, and they keep on increasing. Hence InceptionNet was actually a very well engineered design program, sorry, architecture. So it was very optimized. For that time it was a very well engineered architecture which gave not only very good accuracy, but at the same time it decreased the trainable parameters by a lot. So now let us understand about InceptionNet. The main idea behind InceptionNet is basically for going deeper we should try going wider as well. So let me explain this more in details with the diagram here. So this was the basic naive InceptionNet module. Okay, we'll understand this first because this was the one that was used a lot, and then we'll go and understand one with dimension reductions. So what basically it meant was, let's suppose here you have two images. The main idea behind InceptionNet was despite the size of the image you might still be able to find an object. So let's say here you have a figurine. Now here you have the same figurine, but it's just the head this time and it's way closer. So what this does is, if you have smaller convolutions, you are able to capture smaller features. But if you have larger convolution or maybe larger kernels, you are able to capture larger features. So what it does is, it basically divides into different convolutions of different kernel sizes. So the main thing that I was saying is, along with going deeper, we should also go wider. So that was the whole thing. Here, like it is happening, the previous layer we have here, and this is going wider. Then we have finally a concatenation. So you have 1 cross 1 convolution, 3 cross 3, 5 cross 5, and then again 3 cross 3, but this is max pooling here. So now we will understand everything, but this was the main naive version of Inception module. So an InceptionNet has 9 Inception modules, and it has 22 layers, I suppose. And if you add also the max pooling layers, it has 27 layers. Okay, so this is the whole thing about InceptionNet. Also, this was actually designed by Google, and the first InceptionNet is also known as GoogleNet, capital L-E and then net. So now we will understand the one with dimension reductions. So if you remember, when I told earlier when we were learning about VGG, I told that 1 cross 1 convolutions help in increasing non-linearity, but they also help in reducing dimensions. Now we'll talk about that more. So what that means is basically 1 cross 1 will help in reducing the number of trainable parameters while giving us the same results. So what they have done is, instead of using a 3 cross 3 directly, they have used a 1 cross 1 followed by a 3 cross 3. Then here also, instead of 5 cross 5 directly, it has a 1 cross 1 followed by a 5 cross 5, and likewise here. So the whole thing behind this is to reduce dimensions. Now I will explain how this is happening, because you might be thinking, we are adding another convolution layer, how can that decrease the dimensions? It should increase dimensions, right? So here we have a very good example. So we have this input layer here. This is of 14 cross 14 cross 480, and you have 48 filters, and we are directly doing a 5 cross 5 convolution, and we are getting 14 cross 14 cross 48, 48 being the number of filters. If you remember, this is how it is happening. That means the padding is same. So this is the whole thing basically. So let us calculate how we are going to, what number of calculations or trainable parameters will be required. First of all, for each box here, we will be doing a 5 cross 5 filtering for every box in the output. If you remember, if you got one output, you had to put this whole thing in one part here, and then you had to calculate the whole convolution. So you had to do that many calculations. So for each output you had to do the calculation. So that means we have to do the calculation 14 cross 14 cross 48 times, because we are convolving each and every block with the filters to get one block here for the output. Hence we have to do these many times, and since we are using a 5 cross 5 convolution to find one value, and that is, so we have to multiply it with 5 cross 5. So if you remember, let me just go back here. Let's say you had something of this sort, right? So you used to place this here, and after multiplying and addition, you would get one value for the first block. Then let's say it has a stride of 1, you will place this here next time, you will get for the second value, and finally here and for the third value. In the same way, you will place it one downstairs, and in this manner you will get a 9 cross 9. So for every one block we are calculating a convolution here, this, and for this here. So for every one block what we are doing is, we are doing a 2 cross 2 convolution. That means 2 cross 2 multiplications, right? So that means if I have one block here, I'll be doing a 5 cross 5 convolution in this case. But we have 14 cross 14 cross 48 blocks. So I'll be doing 14 cross 14 cross 48, and for each block of 5 cross 5. So that is multiplied. And since we have not one filter but 48 filters, so this will again be multiplied by 48. Now do you understand the calculation of the number of trainable parameters? Okay, so this, after getting multiplied the whole thing, this comes out to be 112.9 million. Okay, so that is a lot. Now let us look how this can be reduced if we use a 1 cross 1 convolution and then a 5 cross 5. So we have 14 cross 14 cross 480, number of filters is 16, and 1 cross 1, 14 cross 14 cross 16. So 14 cross 14 cross 16, this will be multiplied with 1 cross 1, and then that will be multiplied with a 480. So we get 1.5 million here. And in the same way for 5 cross 5 convolution, now this 14 cross 14 cross 16 will pass through a 5 cross 5 convolution with 48 filters. See, the output is the same. From the input, the output is the same. See here. Here also 14 cross 14 cross 480, and you got 14 cross 14 cross 48 with 5 cross 5 convolution and 48 filters. Here also I am doing the same thing, but I am adding another layer of 1 cross 1 convolution. So after doing this operation, this comes out to 3.8 million. Now this is one convolution, this is the other convolution. So we will be basically adding both the number of trainable parameters. So this comes out to 5.3 million. So that is a big difference. That is like by 20 times it actually is less. 112 here and you have 5 here. So it's a lot. So now that this is clear, so that is how we have reduced the number of dimensions, and that is why InceptionNet is actually known as the best engineered or very well engineered model or architecture. So Inception is basically well engineered. That is why, because it has been thought of very well, and it does not actually change the output dimension, it just remains the same. So it has been optimized in such a way. So this was the InceptionNet naive module, and this is the InceptionNet module with dimension reduction. So what they have done is directly doing a 3x3 convolution. Before not doing that, it has done a 1x1 convolution, and then that is followed by a 3x3 convolution. In the same way, 1x1, and that is followed by a 5x5 convolution. So now let us look into the whole model. We know that this is the module that we will be using, but let us look into the whole thing together as one. What is InceptionNet? Right now we just know about the Inception module. Okay, so this was basically the structure that was given in the paper, in the research paper. So this is also known as, like I said, GoogleNet. So it has a convolution. So only in the starting, by the way, only when you start you have a 7x7 convolution. The rest is all 3x3. So you have 7x7 and the stride is 2. Then this gives you the output size. The depth is 1. And here basically what this means is, since you have in this manner, you have a 1x1, you have the previous layer here, and this goes here. Then you have a 3x3. Then here you have a 5x5. And finally you have a 3x3 max pooling, and all these get concatenated. So this is basically an inception module, right? So this is what 1x1. So here whatever will be written will be the number of filters that will be used for 1x1. So this is 3x3 but for reduced module. That means if you add 1x1 here, so that is what this will be used for. This is basic 3x3. This is again 5x5 but with reduce. That means it has a 1x1 before it. Reduce means reducing dimensions, obviously. So then this is normal basic 5x5, and this is the final pool layer, max pooling layer, and this shows the number of kernels to be used, and these are the parameters that have been calculated for each. So this is the whole structure of basic GoogleNet. Here I also have an very good actually image to show the whole architecture. So this is basically GoogleNet. So it starts here. This is the input. It is followed by a 7x7 convolution, like I mentioned, but the stride is 2 here. Max pooling, yeah, there you have the local response normalization. Again, this was used earlier. The newer versions of Inception do not use LRN that much, so it is not that important. Then a convolution, another convolution, and then here you have the first Inception module. The second one, depth concatenation, means basically concatenation of all these layers depth wise, by the way. So then you have this here, and then this goes on. There is some other things that I need to show you, but yeah, let us see. You can see you have 9 inception modules and you have 2 auxiliary branches. Auxiliary branches are branches that have been separated from the actual model in the side to find the loss here. So this was basically done in the training so that it could understand how these modules were working together as a whole, and which module was giving perfect results, and is adding a new module actually worth it or not. So that was basically the whole point of it. So here you have one auxiliary layer branch, and here you have another auxiliary branch. So in the final output here, the final loss was calculated from this softmax 2 and softmax 1 and softmax 0 together. So yeah, so this is the basic network design of Inception V1 or GoogleNet, right? Now let us get back to it. So here the same thing is written, but it has been given values. So you can see inception modules are there, and the final is an average pooling is used at the end. This was basically used to reduce the number of dimensions again. So this average pooling that is given is basically global average pooling. So this helped to reduce the dimensions by a lot. Now this is a finally summary or points that you can take from InceptionNet. So So 128 1 cross 1 convolution layers were used to reduce the dimension and modify the linear activation units. Linear activation units basically means the activations, that is ReLU or TANH or something. Then a fully connected layer of 1024 units and a modified linear unit was used. Oh, by the way, this was trained on the CIFAR dataset. And in the output, it has 1000 softmax. So you can get that. And the auxiliary branches that I was talking about are only used while training. In the testing it was removed, and later on when the new Inception modules came, the new InceptionNet architectures came, what happened was they realized that the auxiliary branches were not helping a lot, so it was further removed. And a dropout is used with 70% probability, so the dropout rate is 0.7. So this was basically used so that we could actually avoid overfitting, because now you can understand we are increasing the number of layers. In VGG the maximum was 19 layers, here we have 27 layers if we also include the pooling layers, so that is a lot obviously. So hence dropout was used to prevent this, to act as a regularizer. Then a linear layer with softmax loss as classification predicts 1000 categories, right? And but it was removed during the inference phase. Like I said, this is known as the auxiliary branch. And the momentum was set to be 0.9 and learning rate was set to decrease by 4% every 8 epochs. So that means it kept on decreasing the learning rate for every 8 epochs. So what was different in InceptionNet was it focuses on going wider as well as going deeper. So this was a very new concept obviously. This was known as sparse convolution also, and this helped in actually understanding in depth more how this can be used, how we not only need deeper models, we can actually try going for sparser and wider models as well at the same time. So this was a very well engineered, that is why I would say very well engineered model. It helped us expose and go deeper, but at the same time it did not help increase the convolutions by a lot, the number of trainable parameters. So this is all about Inception v1. There are other inceptions like I said, and we will be going through them, but not today. Today we will just be understanding about InceptionNet. In the next class we will talk about residual nets. So these are also basic networks and they also have different versions one after the other, but we will understand about residual nets and then we will come back there, and we will also talk something about transfer learning later on in the classes. But that is for today, and keep enjoying, keep learning, and see you the next time.